Okay, now last lecture we stopped at minor head loss, which is give you this equation. You have the KL means your loss coefficient, and your HL is your head loss. Minus means due to the component itself, due to the component that you use, divided by V squared divided by 2G, or another equation is KL equal to 1 minus A1 A2 square. All right. But what is important for your coming final exam, there will be one question from today's lesson will be on the head loss itself. No, sorry, your test 2. Your test 2 will be, not test 2, your final exam. Sorry, your final exam will be one question from here. Okay, last lecture, we also show you why we need to use guide paints. Here. Okay, now this is today is a new chart for you. So technically, we already have some reference value for your KL. So if you're given a scenario in a test or final exam, if you look at the name here, let's say the exam say that the system is using a regular 45-degree threaded pipe or threaded elbow. So means this is called elbow, 90-degree elbow. You straight away refer to this table and use KL value as 0.4. So another one is that if you see the question saying that this corner is using 45-degree elbow with a 180-degree return bend and threaded, then straight away you use 1.5 for your KL value. Again, the famous equation for this session, it will be HL minor equal to KL V square divided by 2G. So again, all this KL value is linked up with the minor head loss. It's due to the minor head loss. So the importance of value of KL is to use to calculate HL. HL minor equal to KL times V squared divided by 2G, fixed already. Okay, and this equation is important to help you to score some marks in your answer also. You write this one, you will score 1 mark minimum. Okay. All right, let's look at one example. Maybe I should. Okay, I'm not sure why I'm not projecting the full. Okay, anyway. All right, pay a little bit more attention because this question is famous for your coming final exam. All right. Now, you are having a closed loop wind tunnel. So we have one of these facilities in our hydraulic lab. But the setting is not like this, but we are having a open loop. This is called closed loop. Why closed loop? Because the air is circulating within the system. As you can see on the right corner, there's a one diagram there. This is called closed loop wind tunnel, and this is a very, very small wind tunnel. So let's look at the question. So we have a closed loop circuit wind tunnel, and the air is happening at standard condition. Okay, now in the exam, we won't tell you what is the value of standard condition. We assume you already know what is standard condition. Standard condition means temperature 15 degrees Celsius, atmospheric pressure at 1 atm or 1 atmospheric pressure, or you can use 101 kilopascal for the pressure. Okay, I repeat. When you see standard condition, it means that you need to use the value for the temperature. The temperature, it will affect two values. One is temperature, one is pressure. Temperature is 15 degrees Celsius, 15 Celsius, and the pressure will be 1 atmospheric pressure or 101 kilopascal. Yeah. Dinesh, what is the standard condition parameter for temperature and pressure? What is the value?
Temperature is 15 Celsius. Pressure is 1 atm.
Okay, good. All right. Now, as you can see, the velocity. Apologize for my bar here. So, but anyway, you can still see what is happening here. You can see that the air is actually circulating inside this wind tunnel, and you give it a point 1, 2, 3, 4, 5, 6, 7, 8, and 9 back to the point 1. There's a fan there. And you can see there's a curvature line here, hairline here. This is called the guide vein, where we guided the flow to flow at a certain direction. There's a guide vein there. So four corner, you have guide vein. So you need to calculate. Okay, you need to calculate something. The flow is driven by a fan, essentially increase static pressure by the amount of P1 minus P9. So there is an increase of pressure between these 2 points. Needed to overcome the heat loss experienced by the float as flow around the circuit. You need to treat the enlarged section from the end of the test section number 6, which is here, to the beginning of nozzle number 4, which is here, as conical diffuser. Okay, treat the enlarged section from the end of test section number 6 here to the beginning of number 4 as a conical diffuser. Okay, KL different 0.6. The loss coefficient for the conical nozzle between section 4 and 5. And the flow straightforward stream are assumed to be, no, I think this one is wrong. This is not 4, this is 7. I think there's an error here. Okay, but anyway, you're given the KL value from 4 to 6. And then 4, 5, there is a KL value here. And the screen also given you the KL. Once you see the KL value, again, KL is only, we use it to calculate minor heat loss. Don't confuse with the major one. We are calculating minor heat loss. So you need to estimate the pressure. How do we estimate the pressure? So you'll be seeing experimental data, like what you see on your screen here, in the table. It means you have area and velocity. So location 1 means point 1 here. The area of this point 1 is 2 meters square. Velocity measured at this point is 11.1 meter per second. And so on. For example, point 2. When you come to point 2, the area will be 2.6 meters square. Velocity measured at point 2 is 8.7. Point 3 will be 3.3 meter square. Velocity will be 7, and so on. So you have a 9-point area and velocity. And given the speed of sound, will be 343 meter per second. Just to give you some hints, in the exam, you need to know how to calculate speed of sound. Okay, you need to calculate speed of sound when we cover chapter 6 or chapter 7 later on. Okay, so when it comes to final exam, we expect you to know how to calculate the speed of sound already. Specific weight given at 15 degrees C, 1 atm standard atmospheric standard condition will be 12 Newton over meter cube. So this one, in exam, you need to refer to a table. Okay, so the objective of the question is to calculate the change of pressure from here. So as you can see, the flow Q through one circle, and there's a change of pressure between 1 and 9. Okay, so what are the steps that we need to do? First, check the flow condition, if it's incompressible or not. Now, if you solve a fluid dynamics question, the first step, if you see a flow, if you see KL, you see friction, this kind of keyword, first step you do is you calculate flow condition. What I mean by flow condition? Meaning you need to pull out the Reynolds number. So because Reynolds number able to tell you what is laminar, what is turbulent. Okay, so first, before that, I introduce you to the Mach number. Mach number given you by velocity divided by speed of sound. Okay, speed of sound. So the first, you need to check where is the maximum speed that you have inside the system. So from the table that you see on the screen here, the maximum will be 60 meter per second. Okay, so section 5 will give you 60 meter per second. And the local speed of sounds will be 343. Yeah? So just give you some hints. Speed of sound you can calculate by square root of rho RT. I think this one you learn in thermo also. Thermodynamics will give you speed of sound. Speed of sound equal to square root rho RT. Rho is the specific weight. R is the Rankine number or gas constant. Temperature, you need to depends on the Rankine. If a Rankine is in the unit of Kelvin, you need to convert your temperature into Kelvin. Okay, it will be something like Newton dot over Kelvin something. All right. So, okay, Dinesh, what is the temperature of the standard scenario or standard condition? What is the temperature in Kelvin?
15 degrees Celsius.
Yeah, 15 degrees Celsius. What is, how to convert into Kelvin?
Plus 273.
So the answer is what?
287. 88. 288.
288 Kelvin. So this, remember, in final exam, there will be a portion ask you to calculate something like this. Okay, just take note. Okay, I just give you some 4 point or to 5 point in your pocket already. Yeah. All right. So you calculate from the velocity from the table. Maximum Mach number you have here will be 0.6 divided by the local speed of sound. Remember this one will be in the meter per second, so will be 0.175. So this Mach number, if the Mach number is less than 0.3, it is fall under incompressible flow scenario. This is a very important statement. Okay. Remember this statement? Cool. This question for you. If you calculate Mach number, if you calculate Mach number is 0.5, can you consider you are having incompressible case? Cool, are you there?
Yeah.
So if you calculate your Mach number 0.5, is it incompressible case? Can you consider your system having incompressible case?
Yes.
Why? Why yes? You read one more time the one that I circle here. Do you understand this sentence or not? Cool.
If the mesh lower than 0.3, then is incompressible.
Just now you mentioned, what is this?
Mesh number.
We call it Mach number, okay? Mach number, not match. It's a Mach number, okay? Yeah. If you later you communicate with foreigner, with foreign scientists, you mention Mach number and Mach number, you're going to laugh. You're going to make our Malaysia shame. Huh? All right. So what do you understand this one? If you answer, you get from your calculation, if your Mach number is 0.5, do you have incompressible case?
No,
Why?
because it's higher than 0.3.
Okay. Okay, now the question, take note now, the rest take note now. The question I asked who just now is very important for your final exam. Okay, if you miss it, you just listen back to the video. Okay, now we already proved that you can use incompressible equation for our solution. Then we will use energy equation. So this is the energy equation. P1 divided by rho, this is the specific weight, plus V square divided by 2G plus Z equal second point plus the HL, the heat loss. Energy equation is important. Okay, so you can say this one also your Bernoulli equation. Okay, Bernoulli can derive from energy equation. Then you look at the system. If you compare we make some modification based on energy equation, because energy equation you're comparing point 1 and point 2. Energy both end will be the same. Point 1 and point 2 will be the same. So if you look at this case at point number 9, point that I highlight in our screen here, you can modify the equation. You are comparing point 1 and point 9. Okay, this is point number 9, because you are looking, the question asks you the pressure changes between point 1 and point 9. So how do you modify? You just change the one on the left if you are looking at point 1, and for right hand side of the equation, you compare the second point. Then you change all the notation 2 to 9, 2 to 9, and for the loss here is, if you compare to the 9 and you look at the direction of the flow, means that there's some energy loose from point 1, point 2, point 3, point 4 until when it comes to point 9, there's some loss there. So you need to add this heat loss inside the energy equation. Make sense? You have to understand this equation. Why you need to add a heat loss here? Because the flow is flowing from point 1, point 2, point 3 until point 9. There are some losses inside there, and you need to balance this energy equation. And because why? Because in our system there's a closed loop and there's no loss of energy. So you can mention like that. Okay, so in this case, if you look at point 1 and point 9, the elevation is same. If you look at point 1 and point 2, the Z is the same. Z1 and Z2 is same. So if you take Z1, you put Z9, you pull to the left. Z1 minus Z9 is 0, so you can cancel, or you can just cancel in the equation. Velocity at 1 and 2, 1 and 9 will be same, so you can cancel this one, cancel this one. Okay, this is a very important assumption. Then you will arrive at this equation. P1 divided by specific weight gamma minus pressure 9. Pressure at 0.9 divided by specific weight equal to heat loss from 0.1 to 0.9. Okay. And I move forward. After that, we need to calculate two scenario. One is the actual heat raise by the pump or by the fan. this one. Given you, you need to use the equation. And the direction of calculation for 0.1 to 0.9, for the first one is 9 to 1, meaning you are looking at 9 to 1 by the fan means you are looking at the red color arrow. Okay, so you write the energy equation, you modify based on the scenario. The HL will become the heat race because of the fan. Okay, the fan is generating some energy to maintain the speed of the airflow. So you modify HL to HP. Same if you're comparing 0.9 to 0.1, the elevation still same, velocity still maintaining. So you can cancel this one, cancel this one, cancel this one, cancel this one. And it will arrive at second equation. P1 minus P9 divided by gamma equal HP equal to your heat loss from 1 to 9. Next, we look at what is the actual pressure supply to the air. We call it horsepower. We label as PA. We use this formula. So this is also another important formula to calculate actual power supply or power in the unit of watt. Okay. This is gamma, specific weight, or specific gravity, or you can call it specific weight. All right. Q is mass volume flow rate. How to calculate Q? Still remember how you calculate m dot? M dot equal to rho AV. How do you write m dot equal to Q? Rho Q. So Q equal to area times velocity. So Q in the exam will not be given, but you'll be given velocity. You'll be given velocity and area because the table just now, there's a reason why you're seeing area in the question. V times A times HP. Your velocity and area was given in the table just now. Okay, there's a table given just now. This one. Okay, this table. You have area, velocity. Okay, we continue. So you convert your Q into VA. Because the maximum speed that we need to maintain is the test section here in the wind tunnel. Maximum is 60 meter per second. Area is given in the table. So this value is given, this value is given. This value in the test is referred to table. Okay, table for air because we are using air. So there's a table for air. How you see the table of air? If you still have the test 1 paper, it's just behind the after the question, there is lots of reference table there. There's a table for air with temperature and all the parameter from 0 degree to 100 degree C. There's lots of parameter there. One of it is your specific weight. Okay. Then you need to calculate your HL. Okay. Now, KL for each side of the KL here, the KL for the guide vane, we assume the value is 0.2 by using what we cover in the lecture. There's a experimental data collected for the vein guard just now. There's a chart for the vein guard, gut veins. Here, if you look at the lecture, there will be here these slides. If you have a vein guard, your KL value is near to 0.2, so we'll use this value in our analysis. Okay. So remember, important formula to calculate head loss at the corner. HL equal to KL V squared divided by 2G. Velocity given, gravity used 9.81. KL is this one. So you have 4 corner. 1, 2, 3, 4. Later you need to add all the KL together. Okay, so this one is a turning corner. So we can convert the equation. Rewrite the equation HL equal to 0.2 V squared divided by 2G. Since we having an incompressible case, how you know that we having a compressible case? What is the Mach number value?
If lower than 0.3.
Correct. Remember, this is important for your final exam. So, since you're having an incompressible case, then you can use incompressible means you cannot press the air. So your Q will be the same. Q inside the system will be the same. So you can use V equal to VA 5 divided by A at any point. Okay, so that's why you can use this equation. All right. So again, this V you can compare to any point inside the V. You just put V divided by A. You can put any point. Let's say I just label A here. A means you can replace with any point here. The ratio will be the same. Since you're looking at point number 5, because point number 5 is the maximum velocity here, so the ratio will be the same. All right. Then you treat your KL diffuser, the conical diffuser KL value is 0.6. So again, you have another head loss due to the diffuser. So you continue to write HL equal to KL V squared divided by 2G, but in this case, we are referring to diffuser. So minor head loss is it is calculating if you have a component. For example, this one. This one consider 1 component, 2 component, 3 component, 4 component. Then you have a diffuser at the section 6, maybe here. So here also have another KL value and so on. Yeah. So diffuser, we have the 0.6 already. Then you have other value given in the question. For example, the nozzle, screen, KL also have this. So to calculate your total head loss, you need to add all the components together. Okay, in this case, we have 2 assumptions. We ignore head loss in the test section, means we have a smooth surface inside test section. And also, we do not look at major losses. In this case, we focus on minor losses only. So, how you calculate the total head loss? You have how many corner? You have corner 7, which is here. Corner 8, which is here. Corner 2, which is here. Corner 3, which is here. Diffuser, which is here. Nozzle, which is here. Screen is here. Okay, so we ignore this. If KL value doesn't give you, then you don't need to calculate. So because all these are having a KL value. Okay. So you know how to calculate already, yeah? Means you add all the KL together, because for example, corner you have, what is the formula for HL? HL equal to KL V square over 2G. So for the first one, corner, we know that corner is 0.2. So 0.2 velocity, you know, over 2G. Velocity, in this case, we use 60 for all the scenario. So then this one corner also 0.2 V square over 2G. This one also same. This one also same. Diffuser is 0.6 just now. V square over 2G. Nozzle given. Nozzle K is 0.2. Screen is 4. So you add all the value together. For example, after you add, the unit for head loss is a unit of meter. Okay. So just for illustration, you calculate the number. Okay. I don't have the value here. For example, the first corner, you get 10 meter. It will be the same for corner 10 meter. Corner number 2 will be 10 meter. Corner number 3 will same, because the formula still same. KL V square over 2G. The KL value for corner is same. You have 4 vein guide, the guide vein there, same. Okay. Then this one you also calculate, you get, let's say you get 15. Nozzle, let's say you get 8. Screen, let's say you get 20. Let's say lah. So you add all the number, you get the value here. For example, 10, 10 plus 10 plus 10, you get 40 and so on. Okay, 60, 68, 78, 83. For example, you add all this number, you get 83 meter, for example. Okay, so important formula for calculating HL. Once you get this one, you pull the equation, change of pressure equal to rho HP, because just now you already derived the equation. This one. Okay. Previously, when you use the energy equation, here, just now you already developed the equation. P1 minus P9, you factor the gamma out, you pull to the right, you get specific weight times the HL. Or another one, you get HP times the gamma equal to 1 minus 9, same. Huh? So from here, you can calculate the pressure by take the specific weight times the value you calculate just now, the head loss. You'll get the change of pressure from 0.1 to 0.9 in Pascal. Okay, kilo, I just put a kilo there in case you calculate. All these, all right, so just let you know lah. Remember the unit, the pressure is, let's say you calculate here, you get 1000 Pascal. Then you can write 1 kilopascal, for example. All right. Then the next equation you have is the actual pressure will be equal to gamma AVHL. So you calculate, you can also get the PA equal to Newton meter over second. Okay, and then you can convert this one to how many horsepower. Okay, there's a conversion table, convert this unit into horsepower. All right. Okay, with this, I end the lecture.